This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
What that is. It's either Danielle or David here who's running the pass for this course. I'll take that as a no. Okay. Okay, this is going to be the lecture for Programming Fundamentals. Apparently there is peer-assisted study sessions available for this course. I don't know too much about this. I think it's some previous students who studied Programming Fundamentals make themselves available for a study session where you can go and work through problems together, etc., etc. One of them was going to come and give a short talk about it, if not today, then before next week's lecture. So I won't try and discuss it for them. Simply make you aware that this is available, that it's going to be happening, and maybe before next week's lecture we'll have either Danielle or David come to talk about it. All right, I've got to fess up. This is my first time ever in this room. I've got no idea how the screens all work. Does anyone know how to turn that screen on? If not, you people sitting in that area are going to get a crook neck. It should be looking like that all class. All right, no bother. Okay, welcome everyone to the course. My name is Steward1. I have coordinated Programming Fundamentals before, but it's the first time I've been doing the lectures. Other people have lectured it, so yeah, be gentle on me. The lecture slides I'm using were actually put together by Dr. Steward1. So I'm going to be lecturing around the notes that he's provided. Personally, I live in Building W. That's the building on the other side of the high school, in the Institute for Telecommunications Research. My room number is 1-18, I think. I might have put that on the website already. At some point a bit later, I'll set aside a few hours to do consulting each week. So if you need consulting, you can come and visit me in Building W in those hours. Okay. So this apparently is the second programming course most of you will be doing, following on from the problem-solving course. So you should have already been exposed to something like Python. You should already be able to program in a simple language. So we're assuming that you know how to solve problems. In this course, apparently, there's a lot of content. If you fall behind, you're doomed. I think maybe this is Stewart's way of just making you wake up and say, yep, we actually have to work to pass this course. Well, there might be a lot of content in the course. I don't think it's especially hard. I think if you apply yourself, you do the exercises, you write the programs, you should get through okay. Okay, problem solving concentrated on team skills. This is more individual driven. Suggest you form study groups. Blah, blah, blah. Okay, this course is based on the textbook, Absolute Java by Savage. Which looks a little bit like this. Before each lecture, there should be some readings that you have to do. So if you do the reading before you come to the lecture, so much the better. Might help you understand the lecture a bit more. Basically, we're covering the first 12 chapters or so from that book. As well, there will be assignments, each one weighted, I think, 10%. Practicals. Participating in the practicals is part of your assessment component, so you're supposed to come up and actually work in the pracs. And, of course, attending lectures. For support, there are materials, online support. Most of the material you need should be on the course webpage. Google is your friend. If you're sitting at home trying to work out how to do something, type, how do I do X in Java into Google? And you'll be amazed at what comes back. Sites like Stack Overflow, etc., etc. You can be guaranteed that somebody out on the internet has had the same problem as you before. So just type your question into Google. Very high probability that you'll get a good answer. And also Friends Study Group for support. I did also mention before we started the lecture the peer-assisted study program. Peer-assisted study sessions, they'll be made available to you. Danielle and David will talk about that before next lecture. Okay, there's your weightings. Okay, the assignments are 20% each, my bad. Practical attendance 15%. So the idea is you come to the prac and you work, and the practical supervisors see you squirreling away nicely and give you a nice little tick. Some people would be studying this course externally. The fact that you're all here listening to me suggests that none of you falls into this category, but nevertheless, the external students clearly won't be attending the practicals. So for them, what we'll do is we'll open up a little submission portal twice a year, and twice a year they can submit all the exercises they've done to the practical questions, and we can look at them to make sure they've been doing the work. If any of you can't attend the pracs for whatever reason, or you're going to be missing a few weeks, let me know, and I'll also let you submit to this portal that I have for the external students. Okay, but only with my permission. Need to let me know first. Exam 45% at the end. Okay. Academic misconduct. Very simple. Anything you're going to get marks for should not be seen by another student. Penalties apply. Do I need to say more? I think what this means is don't submit the same program as somebody else. There are ways and means of checking source code to make sure that it's original. Do your own work. Don't pay people to do it for you. Don't copy other people's work. Submit your own program. You're much better off failing because you didn't know the work than you are failing because you got caught plagiarizing. So, okay, finger waggled. Moving on. These slides are based on the text. They expect you to have read the text before you see them. Hidden slides are important. Okay, I'm just going to read whatever comes up in front of me here and work off that. If you download this off the website, you should see occasionally some of these appear greyed out. Oh, like that one. So I assume what this means is we're supposed to know the stuff on it. Just Stewart decided not to talk about it in the lectures. So where are we? I do not like PowerPoint. Okay. Much of this lecture is a bit fluffy. I have to talk a little bit about the history of Java, and it's a bit, I'm not really going to be telling you anything that you can't learn yourself from the textbook, but I shall talk around it. So most of you might be familiar with Java as a language for internet applications. Well, back in the day when the internet came in, quite frequently you had to make sure JavaScript was enabled on your browser in order to run certain pages. And these days it all happens behind the scene, but Java was developed, I think, first and foremost for web applications. Nevertheless, Java can be used as a full-blown general-purpose programming language, and we'll be studying Java in that context. The syntax of expressions and assignments will be similar to that of other high-level languages. If any of you has been exposed to the C family of languages, C++ in particular, you'll find Java to be extremely similar. Extremely similar to the point that where the differences are subtle, it's where it catches you, huh? You expect it to be like C++, and it's not. Nevertheless, there are some things that will be quite new. Details concerning the handling of strings, console output, etc., etc. Over that slide. Okay. So Java was created by Sun Microsystems in the early 90s and originally designed for programming home appliances. This was decided to be difficult because appliances are controlled by a wide variety of different computer processors. So if I had wrote a program that had to run on lots of different machines, I would have to compile it separately for each machine. The idea behind Java was to make this a bit simpler and do it in two stages. The first stage, the biggest compilation bit, translates the original program into this thing called bytecode, which is a lot simpler. And then the task of compiler writing just remains to convert the bytecode to operate on each individual machine, okay? So the bulk of the compilation process is done sort of in one hit. The idea that this was going to make Java portable, it was going to make it simpler. The details of this probably don't bother you too much. I mean, when you're writing a Java program, you don't care that it works in a two-step process or not, you just care that it runs. So just being aware of the origins of it, I guess. We've had that slide, haven't we? It's twice, okay. There we are. So like I say, writing a compiler, a Java compiler for every different machine we wanted a program to run on would have been extremely costly. Instead, the developers developed this intermediate language, which is quite low level. It's almost at the level of a machine, called bytecode. So for each individual machine, only a small, easy-to-write program was needed, which translates the bytecode into that machine's native processor language, okay? We're simplifying the process. Patrick McNaughton, Jonathan Payne developed a web browser that could run programs over the internet in '94. That was the beginning of Java's connection to the internet. Netscape Incorporated made its web browser capable of running programs in 1995, and other companies followed suit, and Java quickly became, I guess, the default web programming language at that point. The thing that might be hardest for you to get your head around picking up Java for the first time is the whole concept of object-oriented programming, okay? Java is what we call an object-oriented programming language. It's a programming methodology that uses programmers consisting of objects that talk to each other with methods, okay? There are other ways of programming. The top-down imperative method is whereby we just have a whole lot of instructions. One gets executed after the other. We treat a program like a recipe. It's possible to program in a functional style. All of the program units are functions that get caused by other functions, etc., etc. The particular paradigm behind Java is object-oriented. A program is envisaged as a collection of objects which talk to each other with methods. Objects form the typing mechanism of the language. Objects of the same kind are said to have the same type or the same class. Okay, in other high-level languages we have procedures, methods, functions, sub-programs, subroutines, etc., etc. In Java we use the term method to refer to these types of constructs, and all programming constructs in Java, including the methods, form part of a class. Everything in Java belongs to a class. Okay. There are two types of Java programs, applications and applets. An application is a regular Java program with a method called main, which is what gets run whenever we run the program. All Java applications program have to have a main method. They all start with this. An applet is a Java program that you run inside a web browser. Okay, you can run them off the internet. In developing them, you don't need an internet browser. You actually have this little applet viewer program, which lets you run and debug your programs locally. Applets always use a windowing interface. Okay, they can't be run off the console. Nevertheless, in this course, we're going to be looking just at applications. Okay. And well, here we have a sample Java application program. Whoop. See my mouse up there? Oh, goody. Right. Whoop. So here we have a very simple Java program. You see the very first thing, public class first program. First program is the name of the class. Okay. Then there's a curly bracket, line number 2, curly bracket, line number 12. Everything that happens in between those curly brackets forms part of the class. Okay, and in this simple program there is only one thing belonging to this class. It's a method called main. So this is what gets run when we run the class. Okay. Public static void main string args and some Java code. Down the bottom is what happens when we run this. It prints out, hello reader, welcome to Java. This line prints out, let's demonstrate a simple calculation. The next two lines do a simple calculation. Final line prints out the result. 2 plus 2 is answer. And you see it adds to 4 here. Java programs work by having things called objects perform actions. So in the program we just saw, we saw an object called system.out. System.out is an object which is full of methods for writing output to the screen. Okay. The actions performed by an object are called methods. The particular method that we used in that last example was called println. That was the method or action that the system.out object performs. If I skip back, we see here each line which wrote something began with system.out. I'm telling it what class I want to use, then .println. I'm telling the class what method of that class I'm trying to use. Invoking or calling a method, when an object performs an action using a method, okay? So when I invoke a method, that's also called sending a message to the object. In the example we just saw, I was telling system.out, I want you to print something to the screen. Method invocation syntax in order is an object, a dot, the method name, and a pair of parentheses. If I skip back again, you see that's exactly what we have here. The object, system.out, a dot, the method, println, and a pair of parentheses. Although in this case, we actually had something appear between the parentheses, okay? This is a message we are passing to the object, a parameter. Some methods don't take parameters. In that case, they just have empty parentheses. Right. And well, they're the arguments. 0 or more pieces of information needed by the method are placed inside the parentheses. Oh, look, there it is down the bottom. I didn't have to go back to look at it. So we have object, method, and argument. Okay. In order to use a variable in Java, we first have to declare it. That's not the case in some languages. You don't necessarily have to in Python, for example. In order to declare the variable, the syntax is pretty much identical to the C family of languages. You give the type of the variable, followed by the name of the variable, and a semicolon, or possibly a comma, followed by more variables. So here we have int answer. I'm declaring a variable whose name is answer, and I'm declaring its type to be int. In Java, the equal sign is used as the assignment operator. So once I set up a variable, I can assign values to it. What appears on the left side of the equal sign is assigned to the value of the expression on the right side. So in the example we see here, On the right side of equals, we have 2 plus 2. That's an expression. That gets evaluated. In this example, it gets evaluated to 4. And the number 4 gets assigned to the variable answer. Okay, in Java, the plus sign can be used to denote addition. As we have here, it's adding 2 integers together, or concatenation. Concatenation is what happens when you put 2 strings together. If I join 2 strings, that's concatenation. So, excuse me. The example down the bottom here actually does something kind of nifty. We see inside the brackets here, the parameter I'm passing to println is actually an expression surrounding plus. The left-hand side of plus is a string, and the right-hand side of plus is our variable answer, which is an integer. How do you add together a string with an integer? You can't. So what Java does is it recognizes one of these things as a string, the other thing as an integer, and it says, okay, I'm going to convert this integer to a string. So in this particular example, answer gets treated like a string with 4 in it. That gets concatenated onto the end of this. So here it is again in the program. The string 2 plus 2 is getting concatenated with answer. Java says, hang on, answer is an int. I'm going to make it into a string. And down the bottom we see the output. 2 plus 2 is 4. So Java is what we call a high-level language, right? It's a language that human beings read, write, understand, debug, do programming language fundamentals assignments in, and generally have lots of fun with. Machine language is a low-level thing, right? That's a language which is native to a computer, a language that the computer can understand. Typically a whole lot of switches that encode simple operations like moving information around memory, adding, jumping, etc., etc. A low-level language is machine language, or anything that's similar to machine language. The compiler translates a high-level language, our Java source code, into an equivalent low-level language program, okay, the bytecode, which gets executed. And this translation process is called compiling, or compilation. As I've said several times in this lecture already, compilers, for most programming languages, take a high-level program and they translate it directly to the machine language of the target computer that's going to execute on. Okay? And since different computers have different machine languages, built with different chipsets, etc., etc., we need a different compiler for each one. By contrast, as I've already said, these lecture notes do seem to be harping on the point, the Java compiler translates the Java programs into bytecode, which is a low-level language. It's very simple. But it's a machine language for a pretend computer, if you like, called the Java virtual machine. Okay? Each individual target computer I might want to run this on has its own implementation of the Java virtual machine, which can read in the bytecode and run it, basically. Once I compile my Java into bytecode, the Java can then be used on any computer, provided that computer has a bytecode interpreter. So the bytecode is portable. I don't have to recompile it. I can move it from any machine to any machine as I see fit. An interpreter is a program that translates a program written in one language, like Java bytecode, into the machine language for a particular computer when the Java program is executed. So line by line, it reads in the bytecode and executes it on the computer. It's interpreting the thing as it goes. In practice, a lot of Java implementations these days have what they call just-in-time compilation. Interpretation can be kind of slow. So a just-in-time compiler will take the bytecode and do a second compilation process to convert it directly into something the machine can read. But this is an implementation detail. As I've said before, much of this is kind of abstracted away from us as programmers. You know, we don't care how it happens, so long as it does happen. So code. The term code refers to a program or part of a program. Essentially any text which is Java source is code. A program written in a high-level language such as Java is source code or source program. This forms the input to the compiler. The compiler chunks away on our source code and spits out object code. Object code is the translated low-level program that gets executed on a low-level computer. You could look at the bytecode produced by the Java compiler as object code for the Java virtual machine. You could also treat it as the code which gets interpreted by the Java bytecode interpreter, which runs the virtual machine. Okay. Java programs are divided into smaller parts called classes. We've mentioned that before. Everything in Java is a class. When I write a program in Java, I'm actually putting together a whole suite of classes which do certain things, talk to each other in certain ways. The way this is done in Java is each class has its own separate source file and gets compiled separately from all the other classes. A class loader then, upon running a program, the class loader grabs all the classes I need, the compiled classes, to run that program and links them together. So in other programming languages, this process would be called linking. Having compiled, you link together the object code to run it. In Java, we refer to this as class loading. All right, we differentiate now between syntax and semantics. Syntax being the arrangement of words and punctuations that are legal in a language, the grammar rules of a language, and semantics being the meaning of things written while following the syntax rules of a language. So English, for example, is a language, and it has certain syntax. The quick brown fox jumps over the lazy dog makes sense. Fox quick lazy jumps, brown dog lazy, Java bytecode makes no sense. It doesn't follow the rules of the language. You know, in English we have rules. A subject has to be followed by a verb, followed by an object. An adjective has to appear before a noun. In other languages it's different. En français, par exemple, the adjective typically comes after the noun, okay, with a few exceptions. And Java too has its syntax. We've already seen an assignment. When I want to assign a value to a variable, I need an equals sign. I need a variable on the left-hand side of that, and I need some expression on the right-hand side. Variable, expression, equals, in that order makes no sense. Doesn't follow the syntax of the language, okay? So syntax is grammar. Syntax is the rules that allows us to put together the Java words in a certain way. Semantics is the meaning of things. When I go answer equals 2 plus 2, you know, syntactically valid, the semantics of that means I'm setting answer to the value 4. The quick brown fox jumps over the lazy dog. The semantics of that describes a couple of canine creatures, one in the middle of the air, soaring over the top of the other. Syntax is the rules governing how it gets put together. Semantics is the meaning. A bug, a mistake in a program. The process of eliminated bugs is called debugging. Okay, various sorts of errors can crop up. Most obvious one being a syntax error, which is a grammatical mistake in the program. Syntax errors will get picked up by the compiler. When I go to compile my Java program, if I have typed answer 2 plus 2 equals, for example, I put the equals in the wrong spot, the compiler will recognize that because it's read something which is gibberish to it, and it will create an error at that point while I'm compiling. Okay, the compiler is usually pretty useful about this. It tries to tell you where the error is. It'll say, I found a syntax error, I found it on this line, and it will try and highlight where the error is. Hint, not all languages are as helpful as Java. You should look at each error and try to understand it. A runtime error is an error that doesn't get detected until a program is run. Okay, you might have a program which is syntactically valid, so the compiler passes it. But you go to run it, and something happens at runtime which makes it keel over. For example, if I take two integers, I set one to 0, and I try to divide by it. That will create an error in Java, a runtime error, okay? When I compile the program, the compiler doesn't know that one of the things I'm going to divide by is 0. All it knows is I've got an integer divided by an integer. At runtime, when one of these integers actually turns out to be 0, it kicks a stink. I should point out this only happens with integers too. If the variables were floating point, real values, for example, you can quite happily divide by 0, but that's neither here nor there. A logic error is a mistake in the underlying algorithm for a program. The compiler can't detect these errors and no error message is generated, but the program doesn't do what it's supposed to do. In the previous example, for example, if I'd printed out, let's look at the example 2 plus 3 equals, and then printed the value of answer, it would be writing out 2 plus 3 equals 4 to the screen. And that's wrong. Okay, so that's a logic error. It was a syntactically valid program, and it doesn't do anything stupid when you run it, but it produces wrong output, so it was a logic error. Perhaps one other comment to make before I go on. If you do get runtime errors, quite often they're to do with user input-output. You can write code as tight as you like, but there's still a weak point in the system often, and that's the human being trying to run the program. You ask the human being to type in an integer, and he types in "Hello, Dolly," and your program crashes. Well, so just be aware of that. When we get round to doing input-output, quite often they can be sources of runtime errors because you don't know what the user's going to do until runtime. An identifier is the name of a variable or other item, class, method, object, etc. defined in a program. Okay, so in the example we saw before, answer was an identifier. Okay, it identified a variable of type int. Now there are rules behind the identifiers. They can't start with digits. All the characters have to be letters, digits, or the underscore symbol. And they can be as long as you like, but they are case sensitive. So capital R rate, little letters rate, and all capitals rate are 3 different variables. I would advise you when writing programs to not even do that. If you have to have 3 variables, make sure they're completely different and not just different case of each other. Otherwise it can lead to confusion. There are some words that you can't use as identifiers. For example, public, class, void, static. These are all reserved words that have special meanings in the Java language, so you can't have those as variable names. And there are other predefined identifiers. They are identifiers, but they're already used. Okay? For example, system. We saw system.out before, so system is a pre-declared thing which exists in Java. String and println. Now, you could quite happily redefine these. Okay? You could declare a variable system to be of type int and assign something to it. But that's not a very clever thing to do. It could be confusing because these words have sort of typical meanings, so try and avoid them. Now, while the rules suggest for an identifier, okay, it can be any combination of letters and numbers, so long as it doesn't start with a number, there are still some conventions which we adhere to be good programmers. We start the names of variables, classes, methods, and objects with lowercase letters. And we, well, if our identifier is composed of several words, then we delineate the words by capitalizing at that point. That's the example we got here. Top speed begins with a little t, and since it's made of 2 words, we capitalize the second one. Excuse me, my mouse is all tangled. That's better. Okay, the names of classes, by convention, start them with an uppercase letter, okay, and otherwise just use the same rules as above. If we adhere to this convention, then when we're trying to debug a very lengthy piece of code, then we can see by looking at it what the classes are and what the variables are, right? All the classes start with a capital, all the variables don't. So if you adhere to this convention, it just makes life a bit easier for yourself. Okay, as mentioned before, in order to use a variable, first we have to declare it. Declaring the variable tells the compiler what kind of data is going to be stored in the variable. The example we had before, we declared an integer. We've got another example down here at the bottom. Int number of beans. We're telling the Java compiler, I want a variable, an integer variable, and it's going to be called number of beans. Now this can be followed by more variable names of the same type, provided I separate it by commas. Second example here, I'm declaring two variables of type double, one weight and total weight, so long as I terminate the line with a semicolon. And I think in Java you can declare variables pretty much anywhere in code that you like, much like C++ in that respect. But again, as a matter of convention, it's a good practice to declare them either just before they're used or at the start of a block if they're going to be used extensively throughout that block. Right. The basic types in Java are called primitive types. So int is a primitive type, a variable of type integer. Double is a primitive type. That's a real value, you know, a double precision floating point value, a number with a decimal point in it, right? And here is a list of all the primitive types in Java. Boolean, there is a particular type for Boolean, which can be either true or false, taking 1 byte of memory. This differs a little from certain other languages. In many other languages, they don't bother supplying a special type for Boolean. Instead, anything which evaluates to naught is considered to be false. Anything which evaluates to anything which isn't naught is considered to be true. In Java, they kind of differentiate. They make it, they force it. If you want to have a true value, you need to have a Boolean variable. All the other types are pretty much identical to what you'd get in the C family of languages. Char, byte, short, int, long, float, double. Each of these with an example of the particular ranges they can have. The one real exception from the C family of languages is that char, the character type, takes 2 bytes. For the simple reason that Java is based around Unicode. Okay? When C, C++, the early languages were developed, the character set used was the ASCII character set, which contains 256 possible characters, comprising all the capital letters, all the lowercase letters, the numbers, the whole bunch of control characters. And you could fit that quite happily into a byte, because you have 256 characters. Unicode includes the ASCII set as a subset, but it includes many, many other character sets, a Cyrillic alphabet, a whole lot of Asian characters, etc., etc. And in order to hold all them, of course, our characters have to be 2 bytes. So chars in Java, 2 bytes, because they're Unicode. As we've already seen, in order to change the value of a variable, we need the equals sign. This consists of a variable on the left side of the operator and an expression on the right side of the operator. That's the syntax that Java requires. An expression consists of a variable, number, or mix of variables, numbers, operators, and or method invocations. So in the example down here, we have 2 very simple expressions. One is just it's not an integer, it's a floating point number. The next one is clearly some sort of variable, okay? We have a conventional identifier here, a number of beings. When an assignment is executed, first the expression gets evaluated, then the variable on the left-hand side of the equal sign is set equal to the value of the expression. So in the example here, when Java comes across this, it takes the variables rate and time, multiplies them together, and takes the result and sets that equal to, sets the variable distance equal to that result, I should say. A variable can occur on both sides of the assignment operator, in the example here. So if I come across this, what happens is I take count, I take its value, and I add 2 to it. Whatever that value is, I then set back into count. So I basically increase the value of count by 2. And the nifty thing about the assignment operator is the assignment operator itself returns a value. It returns the value of the expression. Okay, so what I have down the bottom here is 2 assignments chained together. When this happens, number 2 equals expression. The expression here is itself an assignment. Number 1 equals 3. So it evaluates the expression, 3, sets that into number. Okay, it then returns that. So 3 gets set into number 2. The effect of that statement is to set 3 into both the variables, number 1 and number 2. I would caution against doing that as a matter of course. It can get a bit confusing to have a lot of these things chained up together. Your program readability might be improved if you were to do these things on separate lines. Shorthand assignment notation combines the assignment operator and an arithmetic operator, changes the value of a variable by adding, subtracting, multiplying or dividing by a specified value with the general form variable op equals expression. This will become more obvious on the next slide, but there really should be no space between the op and the equals. I might just jump ahead so we can see what we mean. Where's my mouse? Here we are. On the left-hand side, plus equals is an example of the op equals on the previous slide. Minus equals, times equals, divide by equals, mod equals. So when you see one of these things, plus equals, what that really means, oh, get back. What that really means is take the variable on the left-hand side and add to it what was on the right-hand side, okay? So count plus equals 2 is the same as count equals count plus 2. And the same with the rest. Sum minus equals discount. We take sum minus discount and put that in sum, etc., etc., etc. The only other really interesting example here is perhaps the last one. Amount multiplied equals count 1 plus count 2. It evaluates this entire thing first, okay? So that's equivalent to amount equals amount times count 1 plus count 2 in parentheses. So what that's saying is we add these two together before we multiply, right? Now the type system of Java means that you can't store the value of one type in a variable of another type, okay? In this example here, I've declared a variable of type int called int variable, and I've tried to assign a floating point value to it. Can't do that, not allowed. Okay, you can't store a double into an int variable. To do so would involve losing information. We lose all the decimal information. There are exceptions to the rule. If we go the other way, I declare a variable of type double variable, and assign an int to that, Java will let me do that quite happily. I can store an int into a double. For the simple reason that when I convert an int to a double, I don't lose any information, right? So more generally, a value of any type in the following list can be assigned to a variable of any type that appears to the right of it. So I can assign a short to a long, I can assign an int to a double, I can assign an int to a float. I can't assign a float to an int, okay? Note that as you move down the list from left to right, the range of allowed values for the types becomes larger. Right. If I absolutely have to do it, if I have a float and I absolutely have to turn it into an integer, I can do it. But I have to use an explicit typecast, okay? In that case, in the assignment, we really need a whiteboard in here, don't we? In that case, in the assignment, before I assign one value to the other, I stick the type that I require, the type I require it to be in parentheses in front of it. There should be an example coming up. No, maybe not. Oh, whatever. Moral of the story, read your textbook and learn how to do this. Moral of the story is I can quite happily set an int value into a double. I can't easily set a double into an int. Okay, Java will kick up a stink. If you really have to do it, you can do it. You put a typecast in front of the double value and that will convert it to an integer. Okay, the reason Java makes you use a typecast, I guess, is to make sure that you know what you're doing, okay? Because Signing a double into an int essentially throws away information. We're throwing away all the precision. It makes sure that you know what you're doing, and it's not just doing something behind the scenes. Okay, one little other caveat. In Java, an int cannot be assigned to a variable of type boolean, nor can a boolean be assigned to a variable of type int. Okay. That's worth commenting on, since typically in languages like C, C++, you would use an int or even a char for a boolean. As I said, in those languages, if something is 0, it's false. If something is not 0, then it's true. So in the C family of languages, you can assign, boolean values to ints with impunity, because booleans are ints. Java makes a distinction. A boolean is a special thing. You can't assign them to ints. A constant. A constant or literal is an item in Java which has one specific value that cannot change. You can literally type it in. An integer constant is written just as a number without a decimal point. You type in 10, Java will interpret that to be a constant of type int. Constants of a floating point type can be written in ordinary decimal fraction form, so a number with a decimal point in it. And you can also use scientific notation. So if I type in 3.65 e to the fifth, Java interprets that as a floating point value. That's equivalent to 3.67 multiplied by 10 to the power of 5. Okay. The number before the e can contain a decimal point. The number after the e may not, because the e is giving us a whole number of powers of 10. Constants of type char are expressed by placing a single character in single quotes. There's the Z example there. Constants for strings of characters enclosed by double quotes. We have more than one character that forms a string, we use double quotes. If I was to use double quotes around a single character, like double quote Z, double quote, what I get is a string of length 1, having one character in it. But it's a string, not a character. If I just have double quotes followed immediately by double quotes, I get a string of length 0, the null string. And there are only two Boolean types, true and false. And they have to be spelled as is, with lowercase letters, okay? We can't use 1 and 0. We have to use true and false. All right. I might just pause there for 5 minutes. I think we have a 3-hour slot in which to do these lectures. In most weeks, I don't think we're going to take 3 hours to do the entire lecture. And in fact, this one is going to finish, I think, well before the end of the second lecture. But I'm just going to have a quick break anyway. In the weeks to come, what we might do is, once we get through the lecture material, I might just stay here and do question and answers until people get sick of it. Also, just as fate has it, perhaps unfortunately, we've been given Mondays to do our lectures. And in the first half of the year, we get a heckload of public holidays on Mondays. I think we lose 3 due to Easter and a horse race and possibly a monarch's birthday. I forget what they're for, but we lose 3 of them. To that end, what we might actually do is try and fill up the 3-hour slots by going into the next week's lecture or covering stuff we missed out, okay? So while we have 3-hour slots, they're going to be a little bit flexible. Okay, please, take 5, stretch your legs. Oh.
Can I just have a look at this textbook?
If you can't get the 5th edition, it shouldn't matter. I think the 6th might actually be the current one.
Because I've got like so many versions. Yeah.
You got what?
I've got like 2 different versions. Yeah, the books.
Yeah. Or you might find the fourth one off eBay or something. How do you turn that bastard down? Fifth or sixth shouldn't matter. If you can get an earlier version cheap, that should be fine.
Fifth and sixth.
It don't matter.
Okay,
Honestly. The information is much the same. The reason they put out new editions is to make students buy new textbooks and they can make money. Yeah, go for it.
Thank you.
No worries. Could I get someone to look just outside the door and see if there's anyone else still loitering? Just call them in. All right, let's get going again. Just before I launch into it, testing, 1, 2. Right, I'm going to launch back into it. Just before I do, a student just approached me with a question about the textbook. My edition is the 5th. Apparently edition 6 is the current one. But really, you should quite happily be able to use the 4th edition, okay? So anything from the 4th up is good enough. If you can find an old version a bit cheaper, go for it. Right. Okay, so taking on where we left off, we've just learned about constants, arithmetic operators and expressions, right. Expressions can be formed using variables, constants and arithmetic operators, in case being addition, subtraction, multiplication, division and modulo. Modulo is a remainder on division, okay? If I take two integers, divide one by the other, for example 22 divided by 3, the answer to that is 7, but 22 mod 3 is 1, okay? It's the remainder, the number of times that 3 doesn't go into 22. An expression can be used any place it's legal to use a value of that type, right? If an arithmetic operator is combined with int operands, the resulting type is int. If an arithmetic operator is combined with one or two double operands, the resulting type is double. So what this is saying is if I take a double and add it to an int, what comes out should be double, okay? If different types are combined in an expression, the resulting type is the rightmost type on the following list. Same sort of example as before. If I add together an int and a float, I'll get a float. One exception, if the type produced should be byte or short, the type will actually be an int. Okay. An expression can be fully parenthesized, in other words, write brackets around it, in order to specify what sub-expressions are combined with each operator. If the parentheses are omitted in an expression that contains more than one operator, Java follows precedence rules to determine which operators get applied first. This is like your rules in maths, your BODMAS rules, right? If I have a big expression, I evaluate where the brackets are first, then I evaluate the multiplication and division, then I evaluate the plus and minus. Okay, the rules in Java are similar. Nevertheless, it's best sometimes to include the parentheses, okay, because that disambiguates what's going on. You stick parentheses in it, it makes it obvious what's getting combined with what. There's a display taken wholly from the textbook. The unary operators plus, minus, plus, plus, minus, minus, and bang, get applied first if they're in an expression. Following that, the binary arithmetic operators, multiplication, division, and modulo. Third, the binary arithmetic operators, plus and minus. So you can see at least that much is the same as in maths, right? Multiplication and division gets precedence before addition and subtraction. When the order of two adjacent operations have to be determined, operation of higher precedence is grouped before the operation of lower precedence. So if I have an expression base plus rate times hours, multiplication has higher precedence, okay, so that gets done first. That's the same as writing base plus rate times hours with parentheses around the rate times hours, okay? Parentheses make this happen first. If two operations have equal precedence, the order of operations is determined by associativity rules. So for example, if I have two multipliers, or a multiply and divide. Precedence rules, unary operators are grouped right to left. So if I have plus, minus, plus rate, that gets evaluated from the inside out. Plus gets applied to rate, minus gets applied to the result, plus gets applied to that result. You see how at least putting parentheses around this, it gives you the same answer, but it sort of makes explicit what's going on. This is a little bit confusing to look at. The parentheses tells you what happens first. So often it's better to write code this way. Binary operators, an operator that takes two arguments, they're grouped left to right if they have equal precedence. So base plus rate plus hours is evaluated as base plus rate, then plus hours. That's actually not a very good example, since you consider if the parentheses had been around rate and hours instead, you would have got the same result. To see the difference, imagine this was base minus rate minus hours, and convince yourself that if base minus rate in parentheses is applied first, that would give you a different result to base minus rate minus hours in parentheses. And if you still don't believe it, you can type it into a Java program and see what comes out. Whoop, where are we? Okay, one exception to the left to right rule. If I have a string of assignment operators, they're actually grouped right to left. And they have to be, because when I have an assignment, I need to evaluate the expression in order to know what value I'm assigning. So they get evaluated right to left. N1 equals N2 equals N3, evaluates N2 equals N3, and passes that result to the assignment to N1. When one or both operands are a floating point type, division gives us a floating point type. So here I have a float divided by an int. That gives me a float, 7.5. If both operands are integer types, division results in an integer type. Okay, so 15 divided by 2 doesn't evaluate to 7.5, it evaluates to 7. It has to evaluate to an integer, and the fractional part gets discarded, okay? That's a bit of a gotcha. If you're doing division, be wary if you're dividing an integer by an integer and you're expecting something fractional to come out. If you do care about the fraction, either what you need to do is first do a typecast to cast this into a floating type variable first, or otherwise afterwards use the remainder operation, the percentage sign, which I think comes up in the next slide or two. So yeah, there's your warning again. Be careful to make at least one of the operands a floating point type if you need the fractional portion of an integer division. Right. The percent operator, this is the modulo operator, this is the remainder, okay? This recovers the information you lose after performing that division. Int 15 divided by int 2 gives us the quotient int 7. I've lost the 0.5. 15 modulo 2 gives me the remainder, 1. So 1 on 2, right? 7 plus 1 on 2 multiplied by 2 would give me the original 15. Okay, so that operator is useful if I'm trying to count by 2s, 3s, or any other number, or perhaps put more generally, if I want to determine if a number is a multiple of a given number. So if I use number percent 2, when the result is 0, then number is a multiple of 2. Okay, that's an easy way to check if a number is even or odd. Okay, we've mentioned typecasting before. This shows us how it actually gets done. Typecast takes a value of one type and produces a value of another type with an equivalent value. So if n and m are two integers to be divided, and I care about keeping the fractional portion, well, what I need to do is I need to turn this into some floating point type, like a double. What I need to do is cast one of the two operands into a double before the operation gets performed, okay? And I do that by placing the type I want inside parentheses in front of it. So in this expression I have an integer n divided by, well, what was an integer m, but I've placed double in brackets in front of it. I'm telling Java I want you to treat this as a double. So it will convert that to a double before it does the division. It then sees it's dividing an integer by a double, so the answer has to be a double. And indeed I can set that to ans, which is declared to be of type double. Whoop. Oi. Back. There we are. Okay, that doesn't change what m is. M is still an int. M continues to be an int. What double does is basically creates a double value from that, okay, and just uses that in place of it. When typecasting from a floating point type to an integer type, the number is truncated, not rounded, so this is the same as dividing two ints. If I take a float and forcibly coerce that into an integer by a typecast, that gives me 2, not 3. It doesn't round up, it truncates. Okay, it's another gotcha that you kind of need to be aware of. If we go the other way around, if I have an integer type and I assign that to a type of a floating point, like a double, I don't need to include the typecast. Okay, remember Java, if we're moving to a higher precision type, Java will automatically do that conversion for you. Okay, so this line here, double D equals integer 5, takes the value 5.0 and sticks it into the double variable D. Does that quite happily. In contrast, it's illegal to place a double into an int variable without an explicit typecast. Okay, we saw that before in an earlier slide, I think. It's illegal to take a double and cram it into an int. You forcibly have to tell Java first, yes, I do want this to be an int. Because, you know, you're telling it, yes, I know this loses information. I know I'm going to get 5 out of this, not 5.5. That's what I want. All right. The increment and decrement operators, a couple of little groovy things. These add 1 to the value of a variable or take 1 from it. So if n is equal to 2, then n plus plus or plus plus n makes n equal to 3. If n is equal to 4, then n minus minus or minus minus n changes it to 3. But there is a subtle difference between the two. When either operator precedes its variable and it's part of an expression, the expression is evaluated using the changed value of the variable. So what this is saying is if I go plus plus n, that increases n by 1 and then returns the value. If n was 2, plus plus n turns n into 3 and then returns 3. So here we have 2 times plus plus n is 2 times 3. That evaluates to 6. If either operator follows its variable, then the increment happens after the value is returned. So n plus plus returns the current value of n, then increases it. So in the example, if n is equal to 2, 2 times n plus plus evaluates to 4 because this returns the value of n first, 2. We get 2 plus 2, which evaluates to 4. Then afterwards it increases n, so n becomes 3 after that. Okay, remember, if the plus plus minus minus comes first, the increment decrement comes first. Plus plus minus minus comes after, increment decrement comes after. But I'm pretty sure this is defined only for the integer types. You can't plus plus minus minus a float or a double, just the integers. Right, the class string, which I notice had a little warning attached to it at the beginning of the lecture. There is no primitive type for strings in Java, so this has a bit in common with other languages. In things like languages like C, for example, C doesn't have a string type. Instead, string functionality is achieved by using arrays of characters with a null at the end and a whole bunch of functions written around that concept. In Java, there is a predefined class called string, which gives us all the functionality of strings that we need. Stores strings, processes them, prints them out. And you notice we've written it here with a capital letter, okay? Remembering our convention that classes will get treated capitalized. So string here is a capital letter because string is a class. Objects of type string are made up of strings of characters that are written within double quotes. So any quoted string is a constant of type string. If I type quote, live long and prosper, quote, into the Java compiler, Java treats this as a string of that value, constant. A variable of type string can be given the value of a string object. So below that we have an expression, string blessing equals live long and prosper. You see this has the same syntax as the declaration of variables, primitive variables that we saw before. The class name string followed by the word blessing is telling Java, I want to create a variable whose name is blessing of type string. Then equals is setting the value of that, okay? I'm taking this thing here, which is a constant string, and telling Java that I want blessing to be equal to that. We've encountered concatenation before. If I want to join two strings together, I use the plus operator. So if greeting is equal to hello and Java class is equal to class, then greeting plus Java class is equal to hello class. Okay? If I use plus on numbers, it adds the numbers together. If I use plus on two strings, it joins them left to right. And as we saw before, if I use plus on a string and a number, Java will quite cleverly convert the number into a string first, and then do concatenation. And well, there it is again, down the bottom. String, the answer is, concatenated to an integer, 42, evaluates to the answer is 42. So Java has forcibly turned that into a string and bunged it on the end. Right, a class is the name for a type whose values are objects. So string is the name of a class, right? Blessing, that we saw on the previous slide, is an object of type string. An object is an entity that stores data and takes actions, okay? An object of the string class stores data consisting of strings of characters. So as we saw before on this slide, I'll go back. String is a class name. Blessing is an identifier of a variable. It's an object variable, okay? It is a variable of type object. It's not an int, it's not a float, it's not one of the primitive things. Blessing is an object. And this object stores the data containing, the characters for this string. And the object contains all the methods that one might need to operate on that string. The actions an object can do are called methods. Methods can return a value of a single type and or perform an action. All objects within a class have the same methods, but they might have different data values. So I could have 10 different strings, each one with a different word in it. I could have a string with the word live, a string with the word long, a string with the word and, a string with the word prosper. Each string has different data, live, long, and prosper, but each string has the same operations, okay? It can concatenate with other strings. It can tell me what the second character of the string is. It can convert the string to lowercase. So the idea is that the class defines a whole lot of methods that you can do to a string, a whole lot of operations you can do to it. And an object stores the data particular to one instance of that type, one instance of string. We call the methods by writing the name of the calling object, followed by a dot, followed by the method name, followed by parentheses. Okay, I seem to recall we did this earlier in the lecture. Sometimes referred to as sending message to the object. Parentheses contain any information that we pass to the method, and this is called an argument, or arguments if there is more than one. So the string class contains many useful methods for string processing applications. I don't think the lecture goes through this so much, but inside the textbook in the first chapter there was a fairly lengthy table with a whole bunch of methods that belong to string. I recommend having a look. So a string method is called by writing a string object, a dot, the name of the method, and a pair of parentheses to enclose any arguments. If a string returns a value, then it can be placed anywhere that a value of its type can be used. Okay, so let's look at this miniature little program here and see what's going on. First line, string greeting is hello. I've declared greeting to be a variable of type string, string being a class. And I've assigned its data to be equal to hello. So that string will have data equal to this constant string hello. In count, I'm declaring declaring an int variable whose name is count, and I'm setting it equal to this thing here, greeting.length. Length is a member function that belongs to the string class, okay? And I'm calling it on the greeting object. Greeting.length is telling me I want the greeting object and I want the value of the length method on that object. Length just happens to return the length of the string. That is the purpose of this particular method. And its return type is int. It returns an integer. So greeting.length in this case, should return 5, okay, because hello is a string of 5 characters. That returns an int value of 5 and assigns it to count. The variable count now holds the number 5. Then system.out.println, it prints the string length is concatenated with greeting.length. Okay, we saw system.out.println before. System.out is an object that deals with output. Println is the method which we call to print something to the screen. And then what occurs inside these parameters, what occurs inside these parentheses, rather, is the parameter, okay? What I'm passing to it is a string. The value of that string is what I get when I concatenate this short string, length is, with the integer, greeting.length, which will become a string 5 when I concatenate it. So what I'm doing here is I've actually called 2 methods on 2 different objects to try and orchestrate printing to the screen how long my string is. I hope that makes some sort of sense. Okay, always count from 0 when referring to the position or index of a character in a string. Okay, so no, I was hoping there'd be an example there. Nope. Okay, so this represents what a string might look like in memory. This is also taken completely out of the textbook. The string Java is fun has 12 characters, and they're indexed with the numbers 0 through 11. So J is not the first character, it's not character number 1. A is not character number 2. Rather, we start counting from 0. So J is the 0th character, if you like. A is the first. Think of the number as an offset from the start, all right? So I get J if I offset no characters from the start of the string. The blanks and the periods count as a character in the string, okay? So this is the space character, period character. A string object in Java is considered to be immutable, i.e. the characters in it cannot be changed. This might be kind of counterintuitive. When I have 2 strings together and I concatenate them with a plus, I'm not actually changing either string. I'm creating a new string whose contents are equal to the concatenated bits. Okay, so once a string is created, it doesn't change. You can get its value and use that to make new strings, which might be perturbed values of the original string. There's another class in Java called string buffer that does let you edit the objects. It lets you change the characters within the string without having to create new ones. Quite simply, though, if we want to change the value of a string, what we do is just create a new one and assign to it. The example we have here, string name equals soprano. Okay, so I set up name to be a string variable with this data in it. I can then set that string a new value, and the new value is what I get when I concatenate Anthony onto name. That creates a brand new string that says Anthony Soprano and sets it into name. So it's essentially chucking away the old contents and accepting new contents. Okay, I've already mentioned this before. Java uses Unicode. ASCII was a character set used by many programming languages containing all the characters used on an English language keyboard, plus a few special characters, i.e. pretty much anything you can type on a Western keyboard. Unicode, far more extensive. It includes the ASCII characters, but it includes characters with lots of accents, Asian characters, little smileys and stuff if you look deep enough. Naming contents, okay. Instead of using anonymous numbers in a program, always declare them as named contents and use their name instead. Okay, and you see this is declared kind of funnily. Public static final int inches per foot equals 12. Okay, we've seen declarations before. If I just had int followed by inches per foot equals 12, that would have set up a variable whose name was int, which contained the number 12 in it. Sorry, the name was inches per foot, its type was int, and it contained 12. These words in front shan't go into too much detail at the moment, but static final in particular, I'm telling the compiler inches per foot is not going to change. So if I tried to go inches per foot equals 6, Java would throw a wobbly. Okay, it would say you can't do that. You told me this was going to be static and final. You can't assign to it. So for all intents and purposes, the word inches per foot here is the same as the number 12. Notice the convention. This has been typed all in capital letters, okay? This is so when I'm reading the program I know that I've declared this as a constant somewhere, all right, and it's not a variable that I can write to. So the reason for doing this is, firstly, it stops me from changing the value. Like I said, if I now try to assign inches per foot to a different value, inches per foot equals 6, the compiler won't let me. And the added advantage is that now this doesn't have to change. So say, for example, I was writing a program to do with circles, right? I have a method to compute the circumference of a circle, which is 3.14159 times diameter, and I have a method to compute the area, 3.14159 times the radius, and I could get really funky, have lots of trigonometric characters, all of them using this funny 3.14159. Instead of having to type that out once, I could declare a named constant, public static final double pi equals 3.14159. Then I just use pi in the program, right? The next morning, when I wake up and I turn on the news and I find that the breaking news is they found one of Pythagoras' lost scrolls. He's been having us on all this time. Pi was really 3.2. So I have to change my program. Instead of going through my program, changing every time I typed 3.14159, I just have to change it at the top. And it's changed everywhere. Okay, so that's the reason for using naming constants. If you have a value that's likely to be fixed, declare it as a constant. You can use it everywhere. If it ever does change, you only have to change it once. Makes your program a lot more portable. Just as a footnote, I don't think the value of pi is ever going to change. That was just an example. Ooh, end of slideshow. Click to exit. How abrupt. Okay. Okay, so that was that. If anyone has any questions, now might be a good time to ask it. As I said before, in future lectures, we'll use the time as best we can. We're going to lose a few lectures, so we'll try and catch up in them. And if we finish early, we can just have some question and answer sessions. Okay. Great, good.
Steve?